In this video, we will see how to use a statistical test to compare two survival curves. So a survival curve is a plot where you have time on one axis, on the x-axis, and here you have the probability of survival, or the probability until an event is observed. And the event can be death, but it can be the first time that you first encounter a particular object or whatever. So let's say that you are studying the survival time with two different treatments. So the study spans for 4 years, so it goes up to month 48, and then these are the two survival curves. With one of the treatments, this one, we have after 1 year we have about 94% of probability of survival, while with the other treatment we have about 89, and then after 2 years it is 81, 69, and so on. So we can compute the hazard ratio. The hazard ratio is the hazard is the slope of these curves, and somehow it can be interpreted as the instantaneous probability of the event occurring, and we can compute the ratio between those two instantaneous probabilities and put a confidence interval on top of it. So the confidence interval doesn't include one. So that means that we reject the hypothesis that the event is equally likely in both treatments. And even we can compute a p-value and so on. We will not enter into the specific calculations, only that these things can be calculated. When we do an analysis of two survival curves and we compare them using some test, we are doing some assumptions. The typical ones are that the sample is random, that is, that the sample is representative of the population we want to extrapolate later our results, that we have independent subjects, that we have consistent entry criteria, that we have a consistent definition of the endpoint, that we have a clear definition of the starting point, that the time of censoring is unrelated to survival. So if a person leaves the study, this leave is totally unrelated to the effect of the treatment, and that the average survival does not change along the study. So when we are comparing two, so these are typical assumptions of survival analysis. When we are comparing two survival curves, then there are also some other assumptions. The treatment groups are defined before the data collection began. So it is not valid to take a single group of patients, all equally treated, and then split them in two subgroups depending on whether they respond or not. Groups are defined consistently as data is accrued. So, and at the beginning we may think that this assumption is easy to meet, but let's consider the following example. So let's say that our study spans for several years, and the diagnostic groups must be defined consistently. So for instance, we are comparing the survival of cancer patients with and without metastasis. During the study, we have acquired a new scanner that is able to detect metastasis much earlier. So these patients are moved to the metastasis group. So the people that we are moving now to the metastasis group, they have a smaller metastasis than they had at the beginning of our study. So the survival of the non-metastatic group improves because the patients with the smallest metastasis, they are moved to the other group. But also the survival time of the metastasis group, it also improves because the people that are coming in, they have a smaller metastasis than they had before. So actually the survival time has changed because of the new machine has improved in both groups. So this would be an example of this hazard ratio, the probability of occurring the event has changed over time, and what that was one of the assumptions, that it doesn't change over time, or at least there is a constant relationship between the instantaneous probability, the hazard, at every time. At each time, the ratio between the hazard in one of the group and the other is constant. That is one of the assumptions of some of the tests, not all of the tests, but we need to be aware that some of the tests are doing that assumption. This assumption is called proportional hazards. So if you take the slope of all these of these two curves, the slopes are different, but there is a constant ratio between the two. So the ratio, the relationship between the two is constant over time, and we say that we have proportional hazards, even if the hazard changes over time. And this is an example where we have non-proportional hazards. So at the beginning the ratio is something, later the ratio is something else. And for instance, this is an example. This one could be an example when you're comparing surgery with medical therapy or pharmaceutical therapy. So when you do a surgery operation, at the beginning, so just at the operation time, there is a high initial risk, but later, if everything goes well, then the risk is normally smaller. With the medical therapy, the risk at the beginning is not that high as with the surgery, but later it is higher and higher if the therapy is not useful. So in this assumption, in this comparison, we would be violating the proportional hazards ratio. So if the proportional hazard assumption is accepted, then you may use hazard ratio analysis, that is related to Cox model, that is a regression model. And in this example that we are dealing here, the death hazard in one of the groups is 0.38 lower than in the other group. And this is what you have here. So the hazard ratio, that there is a way to compute that, is 0.38. So that means that the hazard in one of the groups is smaller. In this group, the hazard is smaller than in this group. And you can put always a confidence interval and compute from it the p-value. If you can assume this proportional hazard assumption, then you can use a test that is called the log rank method or the Mantel-Cox method to calculate the p-value. If the hazard is not only proportional but it is also constant over time, then you may also use this technique of ratio of the median survival times. And for instance here, the median survival time is the time at which half of the population is still surviving. So for one of the groups it is 900 days, for the other group it is 2000 days, so it is this one, 2000 days. And then the ratio between the two is 0.41, meaning that the mean or the median survival time in one of the groups is about a half of the median survival time in the other group. Then instead of analyzing the data by taking a fixed probability and then looking at the time, you may take a fixed time. So for instance, if you have two groups, and this is a sex, let's say male and female, you fix time, and then at a particular time you have probabilities. So now you can use all the tools that we had to deal with probabilities between and comparing probabilities between two groups. So you can construct confidence intervals. These are these bands that they are called survival bands, and you can do a test at this point. So survival analysis is a complicated tool. Isn't it easier to just compute the mean or median survival times, or the 5-year survival, that is a proportion? So the mean survival time has some cons. So for instance, it does not consider the people that have not died or has been censored during the experiment. And also the survival time is not Gaussian, so all the tools that we have to deal with Gaussian variables cannot be used in this context. The median survival time, or the 5-year survival, so this is a time, this is a probability. They solve the problem of not all the subjects dying, but they also have some cons, and in particular they are losing all the information that is contained in the curve. So they are just concentrating in one point of that curve. So for instance, in these two curves, the two curves are very similar up to 9 months, but then they start to differ significantly. So if you just look at one point, for instance, this median survival time at median, so they are almost the same. So there is the information contained in the curve is much richer than just a single point. There is another problem with survival analysis, that is the intention to treat. So let's say that you are making a study that randomly assigns patients with severe angina to surgery or medical treatment, or medical pharmaceutical treatment. Some patients assigned to surgery, they die before being operated. So should we remove them from the analysis as they did not get the treatment we planned? If we think the time between being assigned to treatment and the time that they actually get treated, that is also part of the treatment. So if it takes 3 months to get into the operation room, then that is part of the treatment, if you have not operated that person. So you shouldn't remove them. And the reason is that if you remove them, you would be removing the early deaths from one of the group, but not the other. So this would bias the results in the comparison between the two groups. The intention to treat approach can be summarized as the analyze as randomized, even if you discover later that the patient does not meet the entry criterion. So you wanted to put it into one of the groups because you thought that it met the criteria to get into that group, but then you discover it didn't, but you should keep it in that group. The treatment was not given, even if they stopped the treatment for any reason. And also it is recommended that you do the survival analysis with this approach of intention to treat and removing those patients. And you shouldn't see a significant change between the two analyses. So if there is a change, then that means that there is something that is correlated between the disappearance of people without being treated and the treatment itself. So this is all for survival data comparison, and see you next time.